Hey everyone, and welcome. Today, we're going to dive into something pretty fascinating, the science of how farm animals grow. Now, it might seem simple, they eat, they get bigger, but it's actually an incredible feat of biological engineering, and it's what our whole food system is built on. So let's get right into it.
Have you ever really stopped to think about it? You see a tiny calf, and you just know it's going to grow into this massive bull. But what is actually happening on the inside to make that incredible transformation possible? How does an organism literally build itself, pound by pound, day after day?
Well, this whole journey from that small beginning to a fully mature animal, it's not random in the slightest. Nope, it's a highly regulated, carefully orchestrated, and pretty predictable process. And to really get it, we need to start with a really basic question.
All right, so let's start at square one. What do we actually mean when we say growth? Because it's a lot more than just watching the number on a scale go up.
Okay, the key word on this slide is irreversible. We're not talking about temporary weight gain, like after a big meal. True growth is about permanently building new tissue, and it happens in two main ways. First, you can create more cells. That's called hyperplasia. Or you can make the cells you already have bigger, and that's known as hypertrophy.
The best way to think about this is like you're building a wall. Early on in an animal's life, it's all about hyperplasia. It's like you're just adding a ton of new bricks to the job site. But later on, hypertrophy takes over. You're not adding new bricks anymore, but you're making each individual brick much, much larger and stronger. And here's a really cool fact. For muscle, the number of those bricks, or muscle fibers, is pretty much set right around birth. So almost all the muscle growth you see in a young animal is just hypertrophy, making those existing fibers bigger and bigger.
Okay, so we know growth is about adding and enlarging cells. But does this happen at just a steady, constant pace, or is there a pattern to it? Well, as it turns out, there is a very, very predictable pattern that applies to just about every animal out there.
Now this is super important. What you're looking at here isn't the animal's total weight over time. This is its growth speed, its velocity. And just look at that shape. It starts kind of slow, rockets up to a peak, and then gradually slows back down as the animal gets older. This pattern is universal, and we can actually break it down into 4 clear phases.
Right after birth, the animal kicks into this accelerating phase. This is when that cell multiplication we talked about, hyperplasia, is just in overdrive. That animal is basically a little growth factory, efficiently turning food into new tissue and gaining weight faster and faster every day.
And then, boom, we hit the inflection point. This is the big one. It's that exact moment of maximum growth speed. For a lot of farm animals, this peak happens right around the time they hit puberty. This is when they're packing on weight faster than at any other point in their lives. And for farmers, you can bet this is a super important window for efficiency.
Now, after hitting that massive peak, things don't just stop cold. The animal enters a decelerating phase. It's still getting bigger, for sure, but the pace is finally starting to slow down. Growth is now shifting more towards making those muscle cells bigger and starting to lay down more fat. And finally, the curve flattens out into a plateau. The animal has reached its mature body weight, and growth pretty much stops. From this point on, all the energy from its food isn't for building new tissue, it's just for maintenance. Keeping the lights on and making sure the biological engine keeps running. This universal curve is just so cool, but it immediately begs the next question, right? What's in the driver's seat? What's controlling this whole process? What tells the body to speed up, hit a peak, and then slow down? Well, the first set of answers lies deep inside the animal itself.
So an animal's growth is fundamentally programmed by its internal blueprint. Its genetics, its species, and its breed set the absolute upper limits. Then you have key hormones like growth hormone and other factors that act as the conductors of the orchestra. And of course, the animal's sex and its age determine exactly where it is on that growth curve at any given time.
And that's the key takeaway here. This isn't about one magic bullet or some growth button. Growth is an incredibly intricate dance. It's this complex symphony conducted by the hormone system, the nervous system, and all sorts of local cell-to-cell signals. Everything has to work together in perfect harmony for that animal to reach its potential.
But here's the thing. Genetics are only half the story. An animal can have amazing potential locked away in its DNA, but that potential can only be unlocked if its environment plays along. And this brings us to the supercritical external factors.
The outside world plays a massive role. Nutrition is probably the single most important one. You can't build a big body without the right building blocks, but things like climate, proper shelter, good hygiene, and the animal's overall health are also absolutely critical. Any one of these can put the brakes on and keep an animal from ever reaching its genetic potential.
And wow, this graph just says it all, doesn't it? The top chart, A, shows an animal with all the best food it could want. You see these clear, rapid growth peaks for bone, then muscle, then fat. But look at chart B. That's an animal with restricted food. The curves are all stretched out, delayed, and way, way lower. It's the same genetic animal, but one single external factor, nutrition, has completely rewritten its life story.
Okay, so we've gone through the what and the how of animal growth, and that brings us to the final and most practical question. So what? Why does mastering all of this science actually matter in the real world? Well, it matters because for centuries, we've been using this knowledge to literally shape animals for specific purposes. This table just shows a couple of examples. A Holstein cow is bred for that huge frame to support milk production. An Angus is bred for really efficient muscle growth. And a broiler chicken, well, it's a modern marvel of genetic selection for incredibly fast growth. We are actively managing that genetic blueprint. And this really gets to the heart of it. In modern agriculture, the name of the game is optimizing how fast and how efficiently an animal can build muscle, all while using the least amount of resources, like feed and time. It's a huge balancing act, where this science directly impacts economics and ultimately our global food supply. And this number right here, this is where the science hits the spreadsheet. It's called Average Daily Gain, or ADG, and it's a huge performance metric in the livestock industry. It's the real-world application of that growth curve we looked at. Farmers track this number like a hawk to make sure their animals are healthy and growing efficiently, and they're always making little tweaks to food and care to get this number just right.
You know, understanding the science of growth has allowed us to create these incredibly efficient systems for producing food. But as our knowledge gets more and more precise, it pushes us to ask some bigger questions, doesn't it? How do we balance this constant drive for efficiency with animal welfare? And as we look to the future, how is the science going to help us sustainably feed a growing world? It's a massive question where biology, ethics, and economics all collide.